Hello, everybody. Welcome. Dimensional analysis is a procedure used in science. Dimensional analysis is a procedure used in science to execute the following. One, it helps you to know, to determine the correctness of a physical equation. It helps you to determine the correctness of a physical equation. We already demonstrated this in our last class. Take, for example, let me give a short question. The position of a particle is given by 1, x equal to x naught plus at cubed. 2, x equal to x naught plus vt. 3, x equal to vt plus half at cubed. Now the question is, A, which of the following equation is correct? A says 1 only, B says 2 only, C 3 only, D 1 and 2 only, E 2 and 3 only. Which of this is correct? B? So the question is this. The question is this. The position of a particle is given by x equal to x naught plus at cubed, x equal to x naught plus vt, x equal to vt plus half at cubed. This is at squared, sorry. And the question is, which of the following is correct? The answer is A 1 only, B 2 only, C 3 only, D 1 and 2 only, and E 2 and 3 only. Now let's look at it this way. In order for us to solve this problem, we need to look at the dimensions to see if which of the equation is dimensionally correct. Yes, please?
For 2, do you assume that the acceleration, there's no acceleration or something?
We don't know. All we need to determine which of the equation is dimensionally correct.
Can you assume that one?
No. So let's look at it this way. The dimensions of x is L, x naught is L, the dimensions of A is L t minus 2, t cubed. You realize that this will give us LT. This will give us LT. So number 1, equation 1 is dimensionally inconsistent, right?
I'm a bit confused on how you got to that.
Remember, for an equation to be correct, now remember, for an equation to be correct, the dimensions of all additive terms must be what? The same. When I use the word additive terms, I mean terms that are separated by the plus, minus, or equal to sign. If you look at the equation, x naught, and at cubed are additive terms. If the dimensions of these terms are the same, then that equation is what? Dimensionally correct. But the dimension of x is L, the dimension of what? X naught is L, and the dimension of this expression is LT. Therefore, the first equation is not correct, because it is dimensionally inconsistent. Let's move on to equation 2. If you look at equation 2, the dimension of x is L, the dimension of x naught is L, and the dimension of Vt is Lt minus 1 multiplied by what? T, which is the same as what? L. So equation 2 is dimensionally what? Consistent, which means it's correct. Equation 3, this is L. We just proved in equation 2 that Lt, this is still what? L, right? The dimension of a number is 1. In other words, numbers are dimensionless. So all we have here is Lt minus 2 multiplied by T2. This will go off with this and you're left with what? L. So 2 and 3 are correct. So what is the answer? E. Yes, please.
I object.
Yes, go ahead, please.
For number 2, you don't know the acceleration. Like, if you're assuming that there's no acceleration, right?
But is the equation correct?
Huh?
Is the equation correct?
Just checking the dimensions.
I
It's dimensional analysis.
Say, but it doesn't
No, just answer the question. Is the equation dimensionally correct?
dimensionally, yeah.
Good. Now, how do we interpret the equation? As a matter of fact, please listen. Listen. As a matter of fact, this is the equation of an object with a zero acceleration. Now, the question doesn't say that the particle is accelerating or not. It simply said the position of a particle is given by. So which of this equation is correct? It didn't ask. It didn't say that the particle is accelerating. So answer the question being asked. Don't answer the question that has not been asked. Do you understand? This is critical because you are answering a question that has not been asked. The question was, which of the following equation is correct? And to determine the correctness of an equation, we use dimensional analysis. And the other period, we said that for an equation to be correct, the dimensions of all additive terms must be what? The same. That is the condition for an equation to be correct in physics. I cannot overstress that. Okay? Now let's move on. Now the next use of dimensional analysis is dimensional analysis can be used to derive mathematical expressions for physical quantities, can be used to derive mathematical expressions for physical quantities. Let us do an example. Let's say, now watch carefully, please. Watch. Let's say that a toy car
Oh, a toy car.
is moving around. Listen, a toy car is moving around with a certain speed v, and the toy car is of mass m, a circular track of radius r. And because you have not done circular motion, you really want to know the centripetal force experienced by this toy car.
Hello, how you doing? I need to see this student really quick.
I pull one.
How you doing? Can I talk to you really quick outside? Sure. Thank you.
Now, listen carefully, please. You need to follow me. Thank you. Um, Pay attention to what I'm about to do because this is really important for your understanding of these concepts. This method gives you the ability to derive relationships between two or more physical quantities, even if you don't know the underlying concepts. This is actually this what we're about to do will illustrate the power of dimensional analysis. Now we want to calculate the centripetal force experienced by this car as it's moving around the track. So what are the variables evident? You have its mass, you have its velocity, and the radius of what? The track. All right? So we know that most likely the centripetal force will be a function of the mass of the car, the radius of the car, and the velocity of the car. What we need to do is, all you have to do is set F to be equal to a constant. I'm going to use K to be our constant, multiplied by the mass raised to the power A, multiplied by the radius raised to the power B, and multiplied by velocity raised to the power C. We know that for an equation to be correct in science, the dimensions of the right-hand side must be equal to the dimensions of what? The left-hand side. Yes, please?
How do you know that there's not going to be like a plus or minus sign in the equation?
Now, A, B, and C are what? Just constants. They can be positive and they can be negative. We are going to use the process of dimensional analysis to determine its values. You understand, right? And when you do that, you will discover that they will give you the right values. Just follow this example and see. Yes, please?
Really quick. I think what he was asking is, how do you know if there's no addition?
No, don't always use positive constants.
Wait, like the mass plus the radius plus velocity is what you're asking.
Okay, good. I'm gonna illustrate an example with that, and you will see how. Okay. Now let me be very clear here. Let me be very clear. Those are very good questions, but right now I'm still giving you baby steps. I don't want to just jump into the whole soup. You'll get drowned. So let's take it step at a time. A building begins with a foundation. So let's lay the foundation, all right? So we know that the dimensions of force is mlt minus what? 2. This constant is dimensionless, so we will only put 1. The dimension of mass is capital M. This will be raised to the power A. The dimensions of r, the radius, which is the distance, is L, which is raised to the power B. And the dimensions of velocity is L t minus 1. And all of this is raised to the power what? C. So we now have M L t minus 2 equal to what? M A L B plus C. Do you understand why it's B plus C? Multiply by t raised to the power minus c. If you look at this carefully, you will realize that A is equal to 1. Now, let me say this before I proceed. For this equation to be correct, it means that the exponents of the terms on the right-hand side must be equal to the exponents of the terms on the left-hand side. For this equation to be what? Equal. That is why A is equal to what? 1. And B plus C is also equal to what? 1. At the same time, negative C is equal to negative 2, which means that C is equal to 2. And what does that mean? This would imply that B is equal to negative 1. So if we feed back everything into that formula, the formula for centripetal force will be equal to K m raised to the power 1 v raised to the power 2 all divided by what? R. And sooner or later you will realize that this K is actually equal to 1. So this is just going to be equal to mv squared all divided by R. We have derived this formula for the centripetal force that a car will experience around a circular track, even without doing circular motion.
Wait, but how did you get MLT to the -2?
It's just like
Those are the dimensions for force, right?
Oh, so it's force
So
equals
it
mass
would be like
acceleration.
Yeah.
kilograms, meters, seconds.
Yeah.
Let me do another example. One of the things that when I was growing up I loved to do was to go out, and be in a swing. And most of you here actually enjoy that. Even right now, on the weekends when I have time, I just take my daughter, we sit on the swing and just swing for hours. But the question is, if you are really curious, how does the period of oscillation of this swing depends on the factors? Here we have length. Here you have your weight, or you're on Earth, so we have an acceleration due to gravity. You have your mass. So all of this, let us determine using dimensional analysis how the period of oscillation depends on mass, the length of the swing, the acceleration due to gravity, because these are the eminent factors. We follow the same procedure. We will start first by saying that let t be equal to a constant as usual, multiplied by m raised to the power a, multiplied by l raised to the power b, multiplied by g raised to the power c. The dimensions of t, which stands for time, is just t. All of this will be equal to the dimensions of k is 1. The dimensions of m is capital M all raised to the power a. The dimensions of L is capital L all raised to the power b. And the dimensions of g, which is an acceleration, is L t minus 2 all raised to the power c. Right? I'm going to do something a little which is very logical and sane. I can, that color doesn't work for me. Let me use green. I can look up, there is no M on this side and there is no L. So if I add an M on this side, it will be raised to the power 0. Because anything raised to the power 0 is 1. If I add an L, it will be raised to the power what? 0. Great. T, this will be equal to M A L B plus C T minus 2C. Are we together? What does this mean? This means that A is equal to 0, B plus C is equal to what? 0, and minus 2C should be equal to 1. Using algebra, you can quickly realize that C is negative half, and therefore B is positive half, and A is 0. So we can now replace the values. Oops. We can now replace the values in here, which would imply that, let me go to the next slide, which would mean that T is K, M, what is the value of A? L, what is the value of B? And what is the value of G? So all of this can be rewritten as T to be equal to K raised to the power L over G. This is the period of oscillation of a simple pendulum. We have dealt with simple pendulum already. Just using dimensional analysis. We have not even talked about forces, restoring forces, and all the complicated stuff, but we are able to come out with the equation just using dimensional analysis. Yes, please?
But how do you know that it's the time for one period? How do you know, like, not, what if it's like, it could also, if you use 2 periods, that's the, it could also be t. Like, it's also time.
In other words, we are looking for how the period depends on length, mass, and the acceleration due to gravity. You understand, right? Now, the beauty of this is that this then can give you, with a given length, and remember, with a given length, you can calculate what the period. It turns out that k is 2 pi. You're actually going to determine this experimentally next week. It turns out that k is 2 pi. But what you need to realize is that this formula tells you how the period is affected by what? Length and the acceleration due to gravity. So the method of dimension is really, really powerful because it gives us the ability to derive a mathematical expression that expresses what the relationship between 2 or more physical quantities that you really could not have unless you know the concepts very well. Sometimes you will be given a question and you will use dimensional analysis to what? To analyze that question or even derive the formula that will help you to calculate the answer. And that is why I start off this year with this, because this is the foundation to almost everything that we will do in this class. Now, let me tease you to see your level of understanding. Let's say we have a spring and a mass is attached to that spring of mass m. The spring constant is k. If we extend this spring and let go, what happens? The spring will oscillate. Now we need to find out how the period of oscillation of the spring depends on the mass and the spring constant. The spring constant K is measured in newtons per meters. You can use this to come out with the dimensions of K. So everybody get to work.
What about the length that you pull it out?
The length doesn't matter. Because it doesn't matter the length, it will still oscillate with a given period. Anyway, you can add the length, put L. Let's see what happens. All right? Yes, please?
Don't you need to know how far it's stretched out, like the change in
Yeah.
X?
That's why I put L.
Well, not necessarily the length of the spring, but the
The extension.
Yeah.
So good thought. Let's do this. I like this. I really like this. So let's find out how the period T depends on what are the factors? Mass, the spring constant, how far it's stretched. Let's use L for that. How about that?
Can we use delta X?
Oh, let's use X. Let's keep away the deltas and keep things simple for now. All right? Let's just use X. Everybody get to work. Get to work.
What's the actual 1/2 of the X?
Wait, K and then delta. Oh, right.
Who is finished? Remember the steps. T is a function of M, K, and the X. So this means that T is K, M raised to the power A, K raised to the power B, and X raised to the power C. Your target is to look for the values of A, B, and the C. The K stands for the spring constant, and the unit is Newton per meter, which means that the dimension of K should be M LT minus 2 divided by L, which is just going to be MT minus 2. So those are the dimensions for K. The first is a constant. You could use any constant. I just love K. I don't know why. I've been using problem afresh. All right, we have T, a constant, M raised to the power A, K raised to the power B, X raised to the power C. This would mean that T will be equal to the constant, capital M raised to the power A. Well, this here is 1. MT minus 2 all raised to the power B, and L raised to the power C. Yes, please?
Could you please explain again how do we transfer the K to MT minus 2?
Oh, definitely. K is called the spring constant, which is basically defined as force per unit meter. So the dimensions of K is the dimensions of what? Force divided by the dimensions of what? Distance, which is just going to be MLT minus 2 divided by L. And this will give you M. And your answer will be MT minus 2. So that being the case, we will have here M raised to the power 0, L raised to the power 0, T, all of this equal to M raised to the power A plus B, T minus 2B, and LC. Looking at that equation, for it to be correct, we see that A plus B will be equal to 0. We also see that negative 2B should be equal to 1, which implies that B is negative 1/2. And if B is negative 1/2, this would mean that A is equal to 1/2, and C obviously is what? 0. So A is 1/2, and B is negative 1/2. So T will be equal to a constant. A is 1/2, B is negative 1/2, and C is 0. So T will be equal to the constant, the square root of what? M divided by K.
That was,
You missed the constant.
Pardon?
he didn't have that initial constant in there at the time when I.
Remember, initially the constant was K, so I changed it not to get confused with.
But I'm saying before you added that extra constant,
Mhm.
I asked, my answer that I gave you was square root of M over square root of K. Was it different without that constant?
Yeah, it's different because experimentally, you will determine in class that this constant is 2 pi. So in actual fact, the period of oscillation is 2 pi M over K.
Announcement. Teachers, please check dress code. Thank you. Good.
I think I remember, because you had a K at the beginning, but you didn't mean the same K.
Yeah.
You just meant a proportion.
So, 2 pi is a constant in this case, but on the quiz when we have to derive the equations, we're just to know what that.
Actually, part of the quiz will be to determine the constant.
Okay.
You can easily determine the constant from the data. Let me show you how. Look up, everybody. Let me show you how. T squared is equal to what? A constant multiplied by M over K. Which means that if you determine the period of oscillation for different masses, and you plot a graph of what? T squared against M, the slope will be what? Phi over K. And therefore, from the slope, you can determine the constant, right? Because the spring given to you will have a certain spring constant.
But how do you know it's 2 pi?
The thing is, all right, good question. This actually, please listen. I like that question because it gives you the limitation of dimensional analysis. Dimensional analysis can tell you how two things are related, but it will not be able to give you that particular constant. If I did derive this equation from first principles using an appropriate model, we would have just gotten the constant directly. But we can know the relationship in using dimensional analysis, but it will not give you the value of the constant. Yes, please?
This constant is just because we use like arbitrary units of measurement, right?
Yeah.
I mean, this is
It's just like the constant of integration. It's similar to that.
So this is not required for the quiz.
I will give you a question which will have a constant, but you will be required. I can either give you the constant to determine another constant, or you will use your graph to determine the constant, depending upon the quiz that I give you.
Is that in the book?
Yeah, it's in the book.
Yeah, but I don't know how to do it with the graph.
All right, how much time is left for this class?
2.5 minutes.
All right, now look up, everybody. We have 2 minutes. Let's not waste it. Let us not waste it. Look up. We have shown how you can use dimensional analysis to determine whether an equation is correct. We have shown how you can use dimensional analysis to derive equations. And now I'm about to show you how you can determine certain constants. Take, for example, everybody write this down. Logarithmic functions, trigonometric functions, exponential functions are all unitless or dimensionless. Are all unitless or dimensionless. I just use sign here. It could be cos, it could be cotangent, it could be sec or whatever. All exponential, logarithmic, this include the natural log, they are all dimensionless. Let me show you how it works. If I give you an expression that Q is equal to Q naught e raised to the power a constant divided by t, and I ask you to determine the units of the constant alpha, what do? You recognize that this exponential function is dimensionless, and for that to be dimensionless, the unit of alpha must be the reciprocal for the unit of what? Time. So this is, the unit for alpha will be equal to what? Seconds. Because seconds over seconds will give you 1. You understand, right? If I give you something like this, x is equal to x naught sine omega t, who can give me the unit to omega?
1 over s.
No, we are 1 over s, exactly.